kind of like the quiz. We're looking at gallium, the gallium hydroacid and the aluminum hydroacid. I'm not going to calculate the aluminum again because we did that earlier. So the aluminum, what it's going to have, and its radius is going to be okay. So let's look at the gallium one. So we see a pKa of 2.6. So we know that that's a stronger acid. So then let's see what the numbers here are. Well, for gallium 3, we get argon as the noble gas configuration. Let's see, its atomic number is 31, and its radius is about 62 picometers. Okay, so, and this is why I was like, shoot, I should have calculated the Z effective, because here we have a larger radius, but a lower pKa, so that charge density is actually going to be the major player.
Yeah, I'm going to ask a question. This might be stupid, but like, is there no d orbital here? Because isn't gallium in the fourth row? Like it's.
Let's see here.
Am I crazy? Let me pull up my theory. Because I just did this one for the quiz.
Did I get? Might be just one of those Fridays. Gallium. Ah, yeah. Oh, so we should have. And then your 4P and 4S come off. Okay. No, that's 3D. And then 3D10. Okay. So yeah, it should be there. Let's see. Okay, let's try to remember. Okay, so let's take one of those. Let's calculate that. So let's take one of those 3D10 electrons. So what was the number? Where do we calculate this?
Wait.
Yep. Need my textbook. So we'll skip this one.
All right.
Ready to clear out my notepad. I don't have all those notes from the previous sessions. So I'll check my textbook and get back to you. Cool.
Amphoteric.
Amphoteric, we remember that means that these can be both bases and acids. And really it's kind of straightforward how they react. If you look at your aluminum oxide here, so now you're seeing something called a gamma aluminum oxide. These little references, these gamma, alpha, beta structures, these are crystal references. And it has to do with the placement of a certain ion in the crystal structure and the stability of the structure. So this is your gamma aluminum oxide mixing with water and hydronium. And you can see it's neutralizing hydronium. So in this case, it's a base. Okay. Versus an acid where you have your aluminum oxide and it's neutralizing hydroxides. Now, interesting thing here, you notice how, so this is like kind of like your first foray into coordination chemistry. So we're getting there towards the end of this chapter. And you see how we go from a 6-coordinate environment to a 4-coordinate environment. So what that's going to have to do, so basically what happens as you're getting rid of those waters and you're getting more and more negative charges, you end up getting a pretty strong steric hindrance in there due to all the electrons. So you can no longer support an octahedral system. So this will max. So with only hydroxides, the aluminum is going to max out at a tetrahedral, because otherwise there's just too much steric hindrance involved. And have you studied steric hindrance in organic yet?
We've definitely talked about it.
Okay, so same idea here. I can't shove any more of those in there because there's just too much repulsion. Now over here, I gave you an example of your alpha and your gamma aluminum oxide. So you see, it's a difference in where, and so those dark spots are your oxygens. It's a difference in where they are and the overall structure of the crystal. And you see the much smaller unit cell for the alpha than the gamma. The unit cell, the alpha, is a much more stable compound. So if we look at this, water, for example, is a small neutral ligand, and your aluminum-3 is going to be small with a large relative charge. So that's why your water system is going to take on the octahedral field. Your hydroxide is larger, negatively charged ligand. Why do you think we say it's larger
than water?
Mm-hmm.
Is it like because it pushes everything away from it more? Like,
well, so let's think of the electronic structure as either a balloon or a fluid.
Mm.
What happens if I add more air to a balloon or more water to a bucket of water?
Just like expands?
Yeah, it gets bigger.
Yeah.
So that's what's happening here. It doesn't matter how many atoms are there. The electronic structure of the hydroxide is much, much larger, and we have to take that into account when we think about the size of the ligand. And so that's why there's too much repulsion with the 6-coordinate environment. And so we end up with this tetrahedral environment that's the maximum that the aluminum can actually neutralize. Okay, solubilities of ionic salts. So, in Gen Chem, you had solubility rules. So we're going to talk more about how solubility actually works. So, of course, solubility is the amount of solid that dissolves in a specific amount of solvent. And all of these, this little list here, these are all different ways to express solubility. So, like, when we're talking about mole fraction, you remember, so you take your ion, your salt, it breaks into 2 ions. So 1 mole of that will make 2 moles of ions, and then you can look at your mole fraction of ions in solution, and you get kind of a percentage. Then that percentage will relate back to exactly, well, how much of that original compound is dissociated. These are all measures of solubility. Okay, so sparingly soluble salts. So when you were in Gen Chem, we called these insoluble. All right. So now we're going to call them sparingly soluble because some of them will actually dissolve. So here you have your copper 2 hydroxide. So of course, we want to remember how equilibrium constants work. So at the bottom left, you see the general equilibrium constant for this compound, but then it becomes what we call this KSP. So K of solubility, the solubility product or solubility constant. And from what you remember from Gen Chem, explain to me why that one loses one of the compounds.
Is it just because you're taking out the solid?
Taking out the solid. So the activity of solids and pure solids and liquids is essentially going to be 1. And so if you have the copper and the hydroxide over 1, well, you just get what's on the right. Okay, so here we say the solubility product for silver sulfate is 1.2 times 10 to the -5 of 298 K. What is the solubility of silver sulfate in first moles per cubic decimeter and grams per 100 grams of water. Now, if you just use the KSP, so here's the little trick that you have to kind of suss out from the book that they don't straight out tell you. If you just use the KSP, you're automatically getting moles per cubic decimeter.
Okay.
Okay. Then you would have to change it to grams per 100 grams of water. Now let's actually write out the KSP. Okay, so here's our KSP. Now we want to figure out the solubility. Okay, well, let's go ahead and write out, we're going to need our chemical formula or equation. Probably should have done this first in order to write the KSP, but you know. And now the KSP makes more sense that we have a chemical formula. All right. So when we're looking at this, we can say that so 1 mole of our silver sulfate is going to end up giving 1 mole of our sulfate. So that concentration will be our solubility. And then 1 mole of silver sulfate gives 2 moles of silver. So that's going to give us 2 times our solubility. Does this make sense to you?
Are you're just looking at the like the 2 in front? Is that?
Yeah, think it like if you put this into an ice table.
Mhm.
So it'd be, what is the change?
What is the change?
So it'd be S and 2S.
Okay.
So kind of think of it on that term.
Ice tables are like a deep memory.
Yeah. For some people, they're a bad memory. But
yeah.
The way you can shorten it down is you can say, well, if it's 1-to-1, the concentration I get of the sulfate will give me the number for my solubility.
Sure.
But when I look at the silver sulfate to just the silver, well, I'm going to have to get 2 times that solubility to equal the number of moles of silver I get in solution.
Sure.
So that's the way you're kind of looking at it. And so then what you have is you're going to have 2s squared times s 1.20 times 10 to the negative 5th, or 4s cubed divide through, don't use your calculator.
0.3 times 10 to the negative 5th.
Yeah.
Right. Okay,
yeah,
3 times 10 to the
it
negative
is
4.
actually. So we'll just call it 3 times 10 to the negative 6th. So then we take the cube root. All right, smarty pants, do that one without your calculator.
Okay. 0. Hello? You got it as 3. Cube root of 3? I don't know the cube root of 3.
Oh.
Oopsie. Yeah, I was not going to get 0.014.
Yeah, that's why we have calculators, but you wanted to go and be super good at the first one.
That one was easy. That was 12 divided by 4. I can do that. Okay.
Okay, so now we have the solubility. Now we need to change this into grams per 100 grams of water. So one thing we can know is the density of water is going to be 1,000 grams per cubic decimeter. All right, well, so let's take our 0.0144 cubic decimeter. We want grams of this, so that this compound is going to be 311.8 grams per mole. And then our water's density, this is going to give us 0.00449 grams of our compound per gram of H2O. Okay, well, I want 100 grams of H2O, so I'm going to take 0.00449 grams. Oops. Multiplied by 100 over 100, and that's going to give me 0.449 grams of my compound per 100 grams of water. So that one, you know, the math is easy enough, but you have to be kind of creative in how you get there.
Sure.
Okay, work on this one for a few minutes, see what you can get. Hope we get to the slide in physics where I talk about, I mean, well, some people will care, but I'm able to kind of show you just how cosmic magnetic fields can get. Every now and then I try to put something interesting in, but still only one or two are like, oh wow, that's awesome. The rest of them just look at me like boring, don't care. All right, well.
Yeah, I have a hard time with people who don't like learning just to learn.
Yeah.
Like it's just cool. That's all there is to it.
That's what I always liked about physics. All my classmates, they're just like, well, I just need to solve this problem. It's like, and I was like, you're dealing with forces that affect the very nature of reality. It's like, how do you not see that it's at its deeper level?
Yeah. Okay.
Not exactly.
No. I think I skipped a bunch.
So what do we set up first from here?
You were doing the like ice table thing.
So you don't have to do a full ice table, just kind of remember what the KSP is. You notice how my silver iodine gives me 1 silver and 1 iodine?
Yeah, because it's silver 1.
Yeah, so each constant, well, and so that's the thing. We don't say silver 1, because silver is one of those rare transition metals. That's a common charge.
Common charge.
Mhm.
So, but this is for solubility. It doesn't give me the.
But if I get, so the KSP is just going to be It's going to be that. But if I look at each one of those concentrations, I get 1 silver from 1 silver iodide and 1 mole of iodide from 1 mole of silver iodide. So the concentration of each of those, so if I just calculated the concentration of silver in solution, that would give me the solubility.
Sure.
So that means that's going to be S. And the same is true for the iodide.
Okay.
That's going to be S squared.
Oh, okay. So I just need to put the 2.17 in for that. So it's like 2.17 squared.
And then let's see, grams per. Now one thing you do have to do is this solubility that you calculate. What units will it give you? If we go back up here,
What units will I get for the solubility?
for S, yep,
For moles squared,
moles per cubic decimeter.
moles per cubic decimeter.
Now this number is in grams per cubic decimeter. So the first thing we have to do, I don't know if this is what you were doing. The cubic decimeter is fine. We want it to stay there. Our silver iodide,
Oh, we want to do grams per mole.
that's going to give us okay, now I can just take and put that right in here.
Okay, okay.
Square that, and we end up with 8. And so there's our KSP. We just have to remember that the KSP automatically gives us moles per cubic decimeter for our units, for our solubility.
Okay.
Okay. Now back to some thermodynamic stuff. Energetics of the dissolution of an ionic salt. So we know we can relay everything through the Gibbs energy here. So our Gibbs energy of solution is again going to be our negative RT natural log of the KSP. So that natural log, when you see it in textbooks, it just says natural log of K. It can be any one of these Ks to give you the Gibbs energy of the solution. You can also see that your Gibbs energy of solution is going to end up being a difference between Gibbs energy of hydration and the Gibbs energy of the crystal lattice. So we will end up working through that. Another way we can actually work through things, we may know the Gibbs energy, we can figure out the KSP, because we could say that, well, let's say we are going to move the negative RT to the other side. And then exponentiate. So we can get this expression that we started to become very used to in thermodynamics. However, we may not necessarily know get lattice energy gives energy or hydration gives energy. So again, we're back to stuff that needs deeper research to really start laying down tables of these energies, which sounds boring, but would be very, very core to stuff that's everyone would use. So this looks more advanced than it is. I wanted to try to get, so this, I mean, it's a generalized chemical formula. Your etas are your stoichiometric coefficients. So that's just your coefficient of reactant one, and then you have your coefficient of product one and product two. And then we know that we can figure out our Gibbs energy of solution with our standard products minus reactants. We're going to have to find the Gibbs energy of formation of a lot of these, and then multiply those Gibbs energies of formation by the stoichiometric coefficient, add the products, add the reactants, subtract the two. And then we say, well, what if we don't have the Gibbs energy of formation? Well, this is where you'd be doing, for example, electrochemical research in a lab. You can start to figure out the Gibbs energy of formation due to standard reduction potentials. So I didn't use N for this one because it's not exactly atoms, but Z is your number of moles of electrons.
Okay, number of moles of electrons.
Mm-hmm. F is your Faraday constant.
Is that like, that's just a number? Or
Yep, just a number.
Okay.
And then of course your E, your E with the, we know that superscripted circle means standard state. So that's your standard reduction potential. So you run electrochemical cells, you find out how much energy does it take to actually reduce these compounds at the electrode.
Faraday, same guy as we talked about this.
Oh, yeah. We'll continue on at this point after break, and then spend the rest of our semester really looking at coordination chemistry and organometallics. Then after that, we can kind of go, well, when we get done with that, we can kind of say, well, what does Sonia actually want to learn next? We can jump around from there.
Okay, sounds good.
But here's a table of like standard reduction potentials so that you can kind of get an idea of what you're looking at. But we'll do some calculations with this next time. And maybe I won't have any foibles the next time we meet. But you know.
Yes. I can't believe it's already halfway through the semester. It's crazy.